My name's Pat. So today we are covering nomenclature and the naming of inorganic chemistry compounds. This is one of the more frequently more difficult things that a lot of professors feel students need some work on. It is also one of the probably 5 things you need to take with you from Intro Chem and Gen Chem 1 if you're going to do well in Gen Chem 2. The expectation when you get to Gen Chem 2 is that you already understand all this nomenclature and all this naming. There's not going to be a pause in Gen Chem 2 for you to pick that back up. So this is material that is useful, it is helpful, and you'll continue to use it throughout chemistry. If you go into organic, there'll also be a section on naming of inorganic compounds. So I like to make a chart. And I'm going to start, I'm just going to start with naming. You can call it nomenclature, but that's just a fancy college word for naming. So we have, that's just a quick refresher, we have our periodic table that looks something about like this, and then comes down, goes back up, comes over here. Something sort of like that is our periodic table. And remember, there's a stair-step line here. Our stair-step line on our periodic table is going to start about in here. We're going to come down over. And this is our dividing line between our metals and our non-metals. Now, metals, for our purposes, are always going to be positive. Non-metals are generally negative, but they can be positive in some cases. But generally, non-metals are going to be negative. So when we come into naming, we're going to talk about 2 approaches. One is going to be if you have a metal plus a non-metal. And let's talk about the simplest case first. So case 1, if your metal has only one charge, it has only one possible charge, then what you're going to do is you're going to provide name of the metal plus the non-metal with the ion ending. The most common ion ending you're going to use is typically going to be IDE, as in chloride, sulfide, bromide. It ends in IDE. So our columns that only have, now how do you know what only has one possible charge? Keep in mind this very first column on our periodic table is going to be +1. This next column is going to be +2. Our next column is going to be +3. Then over here on this side, this column usually over here, our noble gases are 0. Our column with fluorine is going to be a -1. Then the next column is -2, then a -3. And you don't make a comment about the column that carbon is in because that would be either a +4 or a -4. The idea being that these metals will drop off 3, 2, or 1 electrons to assume a noble gas configuration. And when they lose electrons, they become more positive because you now have more protons than electrons. Versus your elements that are over here will pick up an electron. They'll pick up 1, 2, or 3 in order to achieve a noble gas configuration because that is the most stable. So in here, these metals in here that I'm going to highlight in green, these are the ones that have multiple charges. These are your transition metals. The only ones in here that are really stable that you can count on is that you can say that zinc is always a +2, silver is always a +1, and aluminum is always a +3. After that, there isn't a good pattern in this area. But this first column being +1, the second column being +2, this third column being +3, that's pretty solid. You can rely on that. So let's look at an example. Let's take silver. Let's take Ag2O. Now this subscript is because silver is a +1, oxygen is a -2, and this, because silver only has one possible charge, it just becomes silver oxide. When we move to our next one, if we had our next one, let's say it was, well, I'll just use sodium. And then Cl, that just because sodium is in this +1 column and only has one possible charge, all I have to do is write the name sodium and then chloride, and you're done. So this is case 1 of metal and nonmetal. Case 2 is if your metal has more than one charge. Now, when you have more than one charge, then it requires more work. So what you're going to do is you're going to write the name of your metal. And then you're going to find out the charge of the metal. You're going to write the charge in Roman numerals. Inside parentheses. Plus the nonmetal with the ion ending. So let's look at an example for that. Let's say we have FeO, and we also have Fe2O3. We need to know the charge. Iron falls in this transition series, in this transition area, transition metals of our metals. And we need to know the charge of our iron. So because we have no charge hanging out up here above as a superscript, we're going to take our first one and we're going to say iron plus oxygen yields 0. Now we don't know our charge of our iron, but oxygen is 1. The only option that you should see oxygen as a -1 is when it's a peroxide. And the most common peroxide you're going to see is hydrogen peroxide, which is H2O2. But for everything else, it's not a peroxide. Oxygen is always a -2. So just like in Vegas, the race doesn't always go to the strongest or the swiftest, but it's the safest way to bet. Oxygen's not always a -2, but in this case, it's the safest way to bet. So we're going to say plus a -2 equals 0. Add your 2, add your 2. This because our iron is a +2, so this would be written as iron, Roman numeral 2, in parentheses, and then oxide. If we were looking at Fe2O3, we would approach that the same way. So Fe2O3 would be 2 irons plus 3 oxygens, all yielding 0. We'd say 2 irons plus 3 times a -2, all equaling 0. 2 irons plus a -6 yields 0. Add your 6 to both sides. Our 2 irons now yield 6. Divide by 2, divide by 2. That means each iron is a +3. So we would call this iron 3 oxide. Now, the same thing that I did here to determine the charge of the metals, you could do that with a polyatomic ion. If you had a polyatomic ion and you had to figure out what the charge is on, say, and we'll talk about polyatomic ions in a little bit later, but I'm just going to show you an example here. We could use the same approach. An ion has a charge, but I can now write this as phosphorus plus 4 oxygens equals a -3 because I have this charge hanging out up top. I would then say phosphorus plus 4 times a -2 yields a -3. Phosphorus plus a -8 yields a -3. Add your 8, add your 8. The charge on your phosphorus is a +5. So this pattern that we use, setting it to 0 if there's nothing, or setting it to the charge, you can use that to determine what the charge is of your least known element. Keep in mind that, yeah, awfully handy to have the algebra to do this. Keep in mind that we're always going to play our oxygen as a -2 unless you see it as per oxide. So this was the 2 cases of case 1. Let's look at case 2. These are going to be where you have you have nonmetal plus a nonmetal. Again, we break it into 2 cases. Our first case, if first nonmetal, if our first nonmetal is solo, then that, again, our first case is our easiest case. We are going to say name of the nonmetal plus, and now you have to add a prefix to tell it's a solo atom. That's what I'm talking about, solo atoms. So if the name of the you have the name of the nonmetal or the first nonmetal plus a prefix to tell the number of atoms of the second nonmetal. With the ion ending. Remember, our ion ending that we're most commonly going to use for a lot of these is going to be that IDE. Let's look at 2 examples. 2 examples that you've probably heard of. We have CO. So we look on our periodic table, we find out that's carbon. It's solo, so that just becomes carbon. And because there's only 1 oxygen, it's going to be carbon monoxide. Comes out of the tailpipe of cars. Not good to breathe. Let's look at another one we've probably heard of, CO2. Again, our first one is solo, so that just gets written down as carbon. This is 2 oxygens, that's going to be dioxide. Carbon dioxide. You could even do this with, say, if you had phosphorus, you had PCl3, that would be phosphorus trichloride. So it's a very stable set pattern. Nonmetal, nonmetal. If your first one is solo, just the name and then a prefix to indicate the number. Now, just like in our other one, Just like in metal plus nonmetal, nonmetal and nonmetal, our second case is more complex. So if the first nonmetal has more than one atom, then what you're going to do is you're going to provide a prefix with the name of the first nonmetal plus, and then you're going to have a prefix, and again, this is to indicate number. Your prefix is indicating your number. A prefix to indicate number the number of atoms of your second nonmetal with the ion ending. Our best example, and a very common example that you see, is N2O5, which would just be written as dinitrogen. Now notice there is no ending on that first one. It's just the same name of the element. It's dinitrogen. Now we're going to say penta or pent to make up our oxygen, pent oxide. Another one that is it's technically correct, but we don't really use it. But some people use it kind of as like a sort of a to be jokey about it. But you have this H2O, which we all call water. But if you're going to go by the International Union of Applied Chemists, IUPAC, Physical and Applied Chemistry, we could call that dihydrogen monoxide. And people will write kind of funny things. You probably say that people write things like dihydrogen monoxide kills more people than any other chemical every year. Well, that's because it's water. And when it kills you, that's usually called drowning. But when you say it, dihydrogen monoxide, that sounds a lot more fancy than just saying water. But the same pattern, we provide a prefix to the H because it's not solo. You always apply a prefix to the second one. So now let's look at our polyatomic ions. Polyatomic ions are atoms that are grouped together that have a charge. So the general pattern is going to be that 8, if it ends in ATE, it has more oxygen. If it ends in ITE, it has less oxygen. And then there's a set of, that's just, I used to call it a baker's 10, but it's actually 11. So there's a set of 11 polyatomic ions. If you know these 11 polyatomic ions, it will make your life so much easier as you go on. So I write them in a pattern. I start on this far right-hand side, and I write PO4, -3, PO3, -3. SO4, -2, SO3, -2, CO3, -2. Then I'll say NO3, -1, NO2, -1, C2H3O2, -1, CN, -1, OH, -1, and the one positive one that you should know is NH4+. Now, all these across the top are going to end in ATE. This series right here is going to end in ITE. So this is phosphate, phosphite, sulfate, sulfite, nitrate, nitrite. This column will end in also, this row will also end in ATE. This is called acetate. You'll probably come across it as acetic acid. It'll be one of the first acids you use. I'm not saying you can stick your hand in 18 molar acetic acid, but you do have acetic acid in your house. It's about 5% solution, and it's called vinegar. It also happens to be an organic acid, but we're not going to get into that. This is CO3, -2. That is carbonate. Carbonate is real. Now, there is no such thing as carbonite except Star Wars and if you're Han Solo. And then down here we have cyanide. That's not good. Don't breathe it. Don't eat it. This is hydroxide. And this is ammonium. So these polyatomic ions, and knowing these polyatomic ions, will probably be 85% or better of a lot of the chemicals you're going to come across in Gen Chem 1 and on into Gen Chem 2. They keep reoccurring over and over and over again. So now let's talk about acids. Acids, if it ends in ATE, it's going to become ic. It's going to now end in ic. If it ends in ATE, it becomes ic. If it ends in ITE, it's going to become OUS. Now, ate and ite mean that they have oxygen. So if your acid has no oxygen, so an acid with no oxygen, and this is going to be an always, it starts with hydro, and ends in ic. Let's look at an example. Let's say we have HCl, and it's an acid, which means it's written to aqueous. So because there's no oxygen, we're going to call this hydrochloric or chloric acid. Another example, H2S. That's going to be hydro, sol, and now you're going to have furic acid. Hydrochloric acid, hydrosulfuric acid. But if we were to have these, the next ones, notice that they now have oxygen. We have HClO3 as an acid. This just becomes chloric acid. There is no hydro because you now have oxygen involved. If you have H2SO4, also aqueous, that just becomes sulfuric acid. No hydro. There's no hydro because it has oxygen. Last bit of naming. Now, when I drew out the periodic table, I had a periodic table kind of like this, came down, over, came up, and right here. This very last column before you get to noble gases is called the halogens. Halogens are very reactive, and so they have a whole host of polyatomic ions that you will see. But there is a pattern to know the names of what those are. Now, the three halogens that you're most going to be concerned about are going to be Cl, Br, and then I. They can combine with 4 oxygens to take a -1 charge. They can combine with 3 oxygens to take a -1 charge. Let me move this up. They can combine with 2 oxygens to make a -1 charge, or 1 oxygen to make a -1 charge. So if we were to try and name them, these two on top, we know are going to end in ATE because they have more oxygen. We're just going to cut it right down the middle. We're going to give the top 2 ATE. We're going to give the bottom 2 ITE. Now, on the end, at the extremes, at the lowest and the highest number of oxygens, we are going to give a prefix to give a further distinction between something with an O2 and something with an O. So the way I think of this is if someone has low blood sugar, what they generally say they have is hypoglycemia. So our lowest number of oxygens, just a single oxygen, is going to be hypo, and then it would either be hypochlorite, hypobromite, or hypoiodite. This would be chlorite, bromite, or iodite. This would be chlorate, bromate, or iodate. And then on top, we're going to make the same distinction. Now, if you have a kid who can't sit still and can't be quiet and can't keep his hands to himself, what you usually say is hyper. And we used to use hyper, but now it has been shortened to just per. So you could have perchlorate, perbromate, periodate. So this ClO4, which is negative, that is perchlorate. Incidentally, a little side note, that's what they actually found on Mars. It finally convinced them that there had been water on Mars, because where you find perchlorates, at least in our experience, you have to have water. And in case you didn't know, there's still water on Mars, it's just not on the surface. And it's not the kind of water you drink. It's the kind of water that makes the Dead Sea look like it's a glass of Ozarka. So you certainly wouldn't want to drink any water you find on Mars without processing it first. But we can also name these. And I'm going to show you one because some people were here on Tuesday when we did this. This is a problem I got wrong over 20 years ago on a test at UT. I was asked to provide the formula for this compound. Now, I read it as periodic acid. And I looked and I had said, well, I have a periodic table, but I've never heard of periodic acid. The way to think of it is it was periodic acid, which means periodate. Because it ends in ate, it becomes ic. So the formula for this wound up being HiO4, aqueous, periodic acid. But when I saw it and I read it, and I'm pretty sure the professor intended this, I did not ask them, but I'm pretty sure they intended it to be read as periodic acid, and I probably wasn't the only person who got that wrong on the test. I can't tell you any of the ones I got right, but I remember that one from years ago when I got wrong. So we can do any of these. These are very handy. Knowing these polyatomic ions, knowing these 11 polyatomic ions here. Just a quick review. For metal and nonmetal, if your metal has only one possible charge, then you're just going to give the name of the metal and the nonmetal with the ion ending, typically "ide." Silver oxide, sodium chloride. Remember that these columns, this first column make sure. This first column is always positive 1. This next column is positive 2. This next column is positive 3. And then over here, you do have some positive 3s. You can't make a distinction about the column that carbon and silicon are in because they are +4 or -4. It depends what they're combined with. But you can say that the column right next to noble gases, the halogens, are most commonly -1. The next column is commonly -2. The next column is commonly -3. Remember that silver, zinc, and aluminum, which get used a lot, only have one charge, so they would all fall into this category. Your metals in this transition area fall into the second category, where if your metal has more than one charge, you need to write the name of your metal with the charge in Roman numerals inside parentheses, and the nonmetal with the ion ending. We have FeO, which is iron 2 oxide, which we can determine using this algebra and assigning our most common charge to our elements that have the least questions about them. We have Fe2O3, which is iron 3 oxide, which you would use the same approach. You can also use that for polyatomic ions. Notice I did use phosphate because phosphate is one of the polyatomic ions we need to know. For nonmetal and nonmetal, notice that if our first nonmetal atom is solo, then we just give the name of the nonmetal and a prefix to tell the number of the atoms in the second. CO is just carbon monoxide. CO2 is carbon dioxide. PCl3 is phosphorus trichloride. But when our first nonmetal has more than one atom, then we have to give a prefix to tell the number of the first one with the name of the first nonmetal, and a prefix to indicate the number of atoms in your second nonmetal with the ion ending. N2O5, very common, pops up on tests. Dinitrogen pentoxide. H2O, yeah, you've seen a lot of those joke things. They are out there with dihydrogen monoxide warning you about the dangers. Well, we're just going to call that water. But when you look at the people who name it, which is IUPAC, their naming convention would say that dihydrogen monoxide is H2O. Technically, it's correct, but we just call it water. We then finished up talking about our polyatomic ions. We have 8 has more oxygen, 8 has less oxygen. When you're first starting on naming these, I'd recommend writing this kind of pattern down. PO4, -3, PO3, -3. Then all your -2s, which are SO4, SO3, CO3. All your -1s, NO3, NO2, C2H3O2, Cn, and OH. And then this is ammonia. Remember, your first row is 8, your second row ends in 8, your third row ends in 8. Now, these are by no means all of your polyatomic ions, but they are your most common ones. We then wrapped up with naming of acids. So if our acid ends in ATE, it's going to be ic. If our acid ends in ITE, it'll be us. Now, an acid with no oxygen, and this is an always, always take it to the bank, cash it, and go on a vacation, forget about it. An acid with no oxygen that is always going to start with hydro and end in ic. And we used HCl, which is hydrochloric acid, and H2S, which is hydrosulfuric acid. But look how close the names are once we have oxygen. We have HClO3, which is our chlorate, so it would become chloric. But because there's oxygen, we drop the hydro. Same thing here, we have SO4, which is sulfate, so it becomes sulfuric. But because it has oxygen, we drop the hydro. We then talked about this very special series at the end, our halogens, which include Cl, Br, and I. The ones with the most oxygen end in 8, The ones with the least amount of oxygen end in "ite." And then I gave you an example of one that I got wrong a long time ago. Another naming, if you had a metal like Ca, just to wrap up naming and give you one more example. If I had CaCO3, yes, that's a polyatomic ion. But because calcium only has one charge, all we have to do is just call that calcium. And since carbonate is already the name of an ion, it's already got the ending on it. So this just becomes calcium carbonate. And I think I talked about this the other day. If you look at your shower head and you see white stuff caked around it, that's because you live in Central Texas and we have very hard water. And that is a buildup of calcium carbonate that is in your water. That's all it is. I appreciate you guys being here. I hope this was helpful. Keep in mind that if you want some one-on-one work, we have many tutors in the Learning Lab who are there and available to help you with chemistry. I'm there, and I'm always happy to help with chemistry. I like there is a pattern to chemistry that I appreciate and that I like, and I find that you're welcome. And I really like it. It makes it a lot less. There's not a whole lot of arguing about chemistry like there is when you get into history and government and things like that. So if you have questions about chemistry, please don't hesitate to ask. You can put my name down, or we have many other tutors across the campuses who can assist with chemistry. I hope this was helpful. I hope you find this helpful in your class. And please come and see us next week when we cover stoichiometry and how to balance different chemical reactions. Thank you.